Hi everybody. Welcome to Module 6. So in this module we're going to be looking at the chemistry of greenhouse gases and how that applies to climate change. And so today I'm going to take you through some of this stuff and kind of show you how to get started with this activity that was posted on Teams. And just give you a couple of reminders as well. This is also the module where we're preparing for the final project and the Leaf Lab. So next week we'll be talking more about the calculations for the Leaf Lab once you have your final products after the experiment. All right. So first, I've got here the activity that's up on Teams. So this is what you'll be working through. There's always a few questions on it, so I want to go through that and make sure everybody's clear on that. One of the main questions that we're going to ask here is, what is a greenhouse gas? And there are some misconceptions here, so I want to make sure that we address this properly. So first, let's talk about something that isn't involved here. This has nothing to do with ozone. It's a common misconception, but there is something called the ozone layer. Ozone is a molecule, O3, and there's some of it up in the atmosphere that helps protect us from ultraviolet light. Back in the 1980s, 70s, 80s, it was discovered that certain chemicals we were using called chlorofluorocarbons, particularly for refrigeration, were causing this to break down and leaving us vulnerable to these ultraviolet rays from the sun. Because of that, in the wake of that, there was a move to ban those chemicals around the world, which succeeded, and the ozone layer is now recovering. So this has nothing to do with greenhouse gases and climate change. It's a totally separate phenomenon. What's happening with climate change is coming from 4 gases, mostly carbon dioxide and methane. Whoops, CH4 methane. So CO2 is carbon dioxide. CH4 is methane. And then also there are some other greenhouse gases, N2O, and water vapor is a greenhouse gas as well. Those two are not quite as important in terms of what they are doing to our climate as carbon dioxide and methane. Carbon dioxide is primarily emitted as a result of burning fuels, burning hydrocarbons. Methane is released both as just a byproduct of methane is the biggest component of natural gas, so gas mining and things like that releases methane. There are also big stores of methane under in glaciers and other places in the earth that can potentially be released. But a big human factor there is livestock. Raising cows particularly leads to a lot of methane in the atmosphere. So these are the greenhouse gases of concern. The greenhouse effect, so I don't want to, we'll just come back to this, is also often misunderstood, so let's clear that up as well. The greenhouse effect has been known for literally hundreds of years, that what happens to the Earth, so here's the Earth, let's see, there's the sun, I know that doesn't really look like the sun, it's just a demonstration, right? So the sun irradiates the Earth and warms the Earth up, right? We know that. But this also happens to all the other planets. Anything that gets light and energy from the sun is getting warmed up. So what's special about Earth, or one of the things that's special about Earth, is that we have this atmosphere that's held to the Earth by gravity. And so what happens is the light in all along the spectrum and the activity will give you some experience with different types of light and the light spectrum in general. But what happens here is the light that hits the Earth is reflected back up into the atmosphere as a lower energy light. And then the gases in the atmosphere, predominantly carbon dioxide, methane, water vapor, and then some other ones, reflect that light back to the Earth. So there's this main light coming in from the sun, reflects off, or the light doesn't really reflect off the Earth. The light's absorbed by the Earth, and then a different type of light, infrared light, is emitted back out. And if we didn't have an atmosphere, that light would just go out to space and nothing would happen. But because we have these gases in the atmosphere, it allows the light to reflect back to us and keep and have this warming effect. So without the greenhouse effect, as it's known, we wouldn't be able to survive on the planet, because the heat from the sun would simply heat up the Earth, and then the literal Earth, like the ground and water and stuff, and then it would reflect out to space. So it wouldn't stay here. The gases in the atmosphere allow some of that heat to stay here and make our Earth habitable. All right, so what's the problem? Well, the problem is if there's too many of these gases in the atmosphere, if there's too much of it, it increases that greenhouse effect. And so now you have more and more light, or more and more energy remaining on Earth, which leads to an increase in temperature. Now, from the standpoint of the planet, like the literal planet Earth, this doesn't really matter. All that happens if stuff gets too warm is all the living stuff dies. So the Earth doesn't really care about that, but as the living stuff, we do. So part of what this module is meant for you to do is to investigate the data behind this stuff, and I'll help take you through that a bit as well. All right, so let's take a look at this activity. So the first thing to understand what we were just talking about is to actually know what a greenhouse gas is and why these particular molecules are greenhouse gases. To do that, we have to know some things about light. So you can follow this link and look at the electromagnetic spectrum. Light can have a whole continuum of different energies. Also, sometimes that is described by their frequency or their wavelength. And so this asks you to look at some of that light and make some distinctions. As with some of the other activities we've done, you should be able to answer these questions just looking at the table from the link there and clicking on some of that stuff. You shouldn't have to go looking up the answers to the questions, because that might not make sense. What you find might not make sense. So I'd rather you try to find your own definition and then use that. So then we're going to talk about infrared light absorption by molecules. So once we know what infrared light is, we can look at how it's absorbed by molecules and whether or not that can help us determine whether those molecules will act as greenhouse gases or not. This one trips people up a little bit, I think because the questions are almost too simple. So let's look at it together. Even not knowing anything about this stuff yet, if we look at A, if 100% of radiation at a particular wave number is transmitted, how much is absorbed? So you may not know what a wave number is yet. Remember, radiation is another term that we should probably mention. We often use it in terms of bad things. We talk about dangerous radiation, like nuclear radiation. Radiation in general is just a general term that means the emission of energy. So the light that comes out of a flashlight or any other light bulb is radiation. It's radiation of visible light. You can also have radiation of invisible light, like infrared light that comes out of your remote control when you push a button. You can have radiation of ultraviolet light. And ultraviolet light and above, as you'll see in part 1 here, is a little bit more dangerous. It's known as ionizing radiation. X-ray and above in energy has enough energy to knock electrons off of molecules. And so if that happens to molecules in your body, like say DNA, it can cause problems. And that's why those types of radiation are known to cause cancer in certain dose levels. So yes, there are dangerous types of radiation, but there are also types of radiation that don't mess with us really. Okay, so back to this question. Not even worrying about the terms you may not know at this point. If 100% of something is transmitted, how much is absorbed? Well, 0% is absorbed, right? If all of it is transmitted, nothing is absorbed. So this is talking about light going through a particular sample. So then if 50% is transmitted, how much is absorbed? I'll leave that to you to answer, but if you think about light passing through something, if 100% gets through, nothing is absorbed. So if 50% gets through, how much is absorbed? I think you can figure it out. Okay. And then we'll compare that to bromine. Of course, this is an older version of this, so it is not on Blackboard. It is on Teams. So you can take a look at that. Okay. So finishing that stuff, you should have a good sense then of what makes a molecule a greenhouse gas. So the next part is kind of part understanding what processes affect greenhouse gases, like what produce greenhouse gases. It's also some practice with writing and balancing chemical equations. So for each of these, you have to do 4 things. Identify the greenhouse gas involved. Label the activity as either a source or a sink for the greenhouse gas. Is the greenhouse gas produced or is it used up? If it's produced, then we call that a source. Right? So produced goes with source, and used up goes with sink. So if you're, imagine dumping something down the sink, right? Get rid of it. So if a molecule, if you imagine a chemical reaction, you've got A plus B yields C plus D. The A and B are used up in this reaction, this example reaction, and C and D are produced. So if A and B are greenhouse gases, A or B are greenhouse gases, that means they're being used up by this reaction. This is a sink. If C and D are greenhouse gases, then they are being produced, and therefore this is a source. You may encounter reactions in here where there are multiple greenhouse gases, and they're both a source and a sink. So they may be a sink for one greenhouse gas, but then a source for a different one. So that's all fair game here. And then third, for anytime there's a source, so anytime you determine that a greenhouse gas is being produced, we want to know, is that anthropogenic? Is that something that is human-made? Or is that something that is just naturally occurring on Earth? And then finally, write a balanced chemical equation to represent each process. The greenhouse gases, the formulas are not given, because by the time you do these, hopefully you will know those. Other molecules and atoms are shown. So I would encourage you to give these a try and then check with me to see if you've gotten them right. We've talked about balancing equations in the past, so I don't feel the need to go through that whole thing right now. But if you have any questions about whether this is correct or whether you're on the right track, I'd like to see your reactions. Certainly this is something that we'll look at again in the final evaluations. So make sure you have those written down somewhere. Excuse me. All right. So that is this activity. The other part of the work for this week is to look through just one section of the IPCC report. IPCC stands for Intergovernmental Panel on Climate Change. The IPCC was developed by the United Nations several decades ago now to study climate change and to be an unbiased group of scientists from all countries, or as many countries as they could, representing the United Nations, to take all of the research on climate change, which is, there's a ton of research. So you're talking about really big teams of scientists, reading, criticizing, discussing, debating all of the research and trying to synthesize it all into a report saying, okay, of all of the experiments, of all the science that's going on, what are the things that we can say we've learned? What is the weight of the evidence showing? It's an amazing, amazing project just in its scale and its scope. So much being done there. Back in the very beginning of class, we talked about the process of science, and we talked about how you need to weigh all the evidence. You can't ever say that you're 100% certain about something. You can say the bulk of the evidence shows this, but then if there's more evidence that refutes it, you have to take that into account. And then you come up with some overall conclusions based on the preponderance of the evidence. Like, what is the overall conclusion that we think based on the evidence? And so every, I think it's 6 years, 4 or 6 years, I can't remember the exact number, this group comes out with another report. They just released the 6th one last year in 2021. And the reports over the years have really, I wouldn't say they've changed, but they've really crystallized the important parts. The early reports were really criticized for being overly vague and inconclusive. Even though it was quite clear scientifically that climate change was happening, it was human-caused, it was a problem, because of the scientific method, there were a lot of places where they had to say, well, I don't know, we don't really know yet if this is caused by climate change or if this is something else. Hang on, I gotta turn the lights on again. But as the reports have progressed, this has become more and more clear. So one big example in this particular report that's changed, that's new, is we've never really been able to associate severe weather events like hurricanes and floods and things like that specifically with climate change. Scientists thought that they were associated and that climate change was making them worse, but there wasn't enough data to really say, yes, these would not have been as bad as they were if we didn't have the climate changing the way it is. And in this last report, there's actually enough evidence now to really say that we can show that climate change actually is right now making these events that are happening right now worse. So that's an interesting conclusion there. So I want to pull up this report in Teams. So I'll have to pause this for a second. All right, sorry about that. I'm back. So here's the part that is linked on Blackboard. This is the Working Group 1 technical summary. So what does that mean? It's still loading, I guess. So the IPCC 6th Working Group is the 6th report, or 6th report is the 6th report from 2021. Sorry, I said that a lot of times. Working Group 1 is the one that we're most focused on. It's the science working group. So it's the group that puts together all of the science that we were just talking about and tries to make some conclusions about what the data are showing. The other working groups are working on things like what are the effects on politics, on governments, on migration, and then there are working groups working on solutions. What do we need to do to solve these problems? And there's all kinds of great work with all of those. But just to give you a sense of the scale of this project. So this is just the very first chapter, basically, of this report, the first part. This isn't even the full chapter. This is just the summary of the chapter, and it is 112 pages. So just to give you a sense of that scale. So let's take a look at it a little bit here. So the authors, right, you've got coordinating authors from all over the world, so people kind of in charge of the project. Then you've got authors who are all significant scientists in their field. contributing authors, who maybe help out here or there. And that's a lot of people, right? And a lot of stuff going on. So what I want you to do is work your way through this. The technical summary is meant to be communicated to a general audience. So it's not scientists talking to other scientists. It's meant to be something the general public should read. That said, it is a technical summary. It does involve the actual data. So it may take you some time to work through and understand it. The other thing is, the 100 and whatever pages, yeah, there's a lot of pictures. So it's not 100 and some pages of just writing like this. There's also references, footnotes, all kinds of stuff like that, charts. So, if you really want to do the least amount of work possible here, which I know you don't, right? You want to do lots of work. But no, seriously, if you're having trouble working through this, all right, a couple not shortcuts, but tips on working through it before you get into the real meat of it. So first, there's this box right at the top, core concepts central to this report. If you don't get anything else, make sure you understand these core concepts. All right? Secondly, updates since AR5. So AR5 was the last report from 2013. So okay, I guess we know the time then. It was 8 years apart. I said 4 to 6. It's 8. So AR5 was in 2013, and this is now AR6. So all of these bullet points here are the updates since that last one. So this is the absolute newest stuff. What do we know now that we didn't know before? And the first one, I think, is of course, the most important. Human influence on the climate system is now an established fact. That is strong language for a science report, right? We talked about uncertainty and blah, blah, blah. But there is so much evidence showing this. I mean, just an incredible amount of evidence that we can really say it is an established fact as much as we can say it is an established fact that matter is made of atoms or something like that. Right? We know about how much global warming there is to date, and some other things. All right. I mentioned the extreme events one. So you can see some of this stuff is bullet pointed, and that'll kind of help you look through it because it organizes it in a way that is hopefully meaningful. If you have questions about some of these words, some of the terms, please post about them on Teams or bring them into class so that I can help you work through this. And then, of course, the pictures are always really interesting because it's a way to show a lot of data in a relatively small amount of space. So let's take a look at just a couple of these. Right, so you may have seen something like this before, where we have global surface temperatures relative to the years 1850 to 1900. So 1850 to 1900 would be right at 0 here. See my cursor? And you can see how it's just absolutely gone up. The comparison here between observed, reconstructed, and simulated gives us a sense of how good our data are. Because of course we've only observed the global surface temperature since, the middle of the 19th century. So we don't have direct observations. These older observations of the temperature come from other types of ways we've reconstructed that through ice core data, things like that. So we can get a sense of how well our observations work or mirror our simulations and reconstructions. Looking for one more picture here to show you. I don't know if it's going to load. All right, well, I may have to show them in class here. So some of the here, well, okay, we can look at this one. So one thing that goes on throughout this report that you should probably know about is that we don't know what's going to happen in the future, of course. So when we try to predict the effects of climate change, we have to make some assumptions. And what this report generally does is looks at the entire range of assumptions. So, what would happen if we all were able to cut our greenhouse gas emissions really quickly? And then what would happen if we could cut them somewhat gradually over time? And then what would happen if we did nothing and just kept going as usual? So you generally kind of see that in three categories. There is no longer any category where everything is fine. It's just too late for that, unfortunately. But we have progressive levels of bad. And we want to reduce those, right? So, for example, if right now we're hopefully worldwide shooting for a goal of 2 degrees change, but realistically we're probably more like in the range between these, 2 and 4. Those don't sound like big numbers, but 4 is really catastrophic if you look what would happen. So with temperature change, you're talking about a massive global temperature change if we get up to 4 degrees C. Precipitation change, huge, right? Massive, massive flooding in some areas and just absolute drought in others. And if you go down to the plus 2 degrees or the plus 1.5 degrees, you can see how those effects are somewhat reduced. Soil moisture change. So when we're talking about droughts, right? You look at like the Western US here, South America, that in these worst scenarios, you have extreme losses of soil moisture. And then extreme flooding in other areas as well. So you can see some of those things from some of these graphs as you work your way through this document. So yes, it's big, but I think you can do it. There's also a video I've linked in there that shows that shows some of the highlights from this, but it's very short. So that's a good place to start, but at least work your way through some of this. One of the things I'm going to ask you in the final evaluation, I'm going to ask you something about this report. So not some specific thing like, what does this little graph mean, but something more general like tell me one of the major things that you took away from this report. What was a graph or a figure that was meaningful to you? What did it show? Things like that. So it is worth making your way through this to understand what's really going on with the climate of our planet. All right, that's all for today, and I will see you in lab.